Sampling. Sampling is basically the process for converting a continuous time domain signal into a discrete time domain signal. So you have been given a CT signal, and through sampling process we can obtain the discrete time domain signal of the CT signal. All the signals in nature are CT signals, right? In order to obtain the discrete version of the CT signal, we need to do the sampling. So how do we perform sampling? Sampling is basically performed by multiplying a continuous time domain signal with a train of impulse. Right? So if we have a continuous signal and we want a discrete time domain signal of it, what we need to do is multiply the signal with a train of impulse. Now what is a train of impulse? Train of impulse is all the impulses put together. It's the impulse at 0 along with all its shifted versions. So this is the impulse which is shifted by a period Ts. This is the impulse which is shifted by a period 2Ts. This is the next impulse shifted by 3Ts. Similarly, this is the impulse which is shifted by minus Ts. This is the impulse which is shifted by minus 2Ts. So all these shifted impulses put together is called as the train of impulse. Right? Now what are we interested is in the period between the impulses. Right? If we multiply the signal, the CT signal with the train of impulse, right? What is the output? Output is nothing but the sample or the magnitude of the input at the time of sampling. So who decides the time of sampling? It is these samples. It is the position of these samples that decides the actual position of sampling. Right? So wherever we have a train, wherever we have an impulse, it results in the output of the discrete signal. Here is an example. So whatever is the magnitude of the CT signal at the instant of this particular sample is the output of the discrete signal. Right? So it is the position of these train of impulse that decides the positions of the discrete time signals, and hence the spacing between the train of impulse is very important. So what is the spacing between the between the train of impulse? The spacing between the train of impulse is nothing but the sampling period. This is very important. The spacing between the train of impulse is called as the sampling period. So this is the sampling period. And if you observe carefully, all these samples are appearing after equal amount of time because we have chosen an equal rate, right? We have chosen equal time period between the samples. So all these samples are appearing after every Ts amount of time. And what is Ts? Ts is the sampling period. We call this period as the sampling period. So all these train of impulses are appearing after equal amount of time, which we call as the sampling period. And therefore, in the DT signal also, the spacing between the samples is the sampling period. So all these samples are equidistant. If you closely observe your DT signal, right, all these samples are equidistant. It means that they are appearing after equal amount of time, because we are uniformly sampling the CT signal. This is very important. We are uniformly sampling the CT signal, and therefore it results in a DT signal having samples which are uniformly placed after every TS amount of time. So all these samples are appearing after TS amount of time, and therefore we call the train of impulses located at 0, located at Ts, located at 2Ts. 2Ts, how do we call it 2Ts? Because with respect to the first sample, this particular impulse is appearing after 2Ts amount of time. With respect to the sample at 0, this sample is appearing after 3Ts amount of time. Right? So all these samples are placed after every Ts amount of time, and therefore as we have the train of impulses in uniform time interval, right, and these position of these impulses decide the position of the discrete time signal. And what is the magnitude of the discrete time signal? The magnitude of the discrete time signal is nothing but the magnitude at the instant of sampling. The magnitude of your CT signal at the instant of sampling. So if I talk about this particular sample train of impulse, then this sample in the train of impulse will give me a sample of magnitude at that instant of the CT signal. So all these magnitudes corresponds to the magnitude at the instant of sampling. So a simple multiplication of a CT signal with the train of impulse results in a discrete time signal. So this process is called as sampling. So the process in which we transform a CT signal into a DT signal is called as sampling. And the period that we decide between the samples is called as a sampling period. This is the period with which the samples appear after this is the period with which the samples are repeating, and this is called as a sampling period. And the reciprocal of this sampling period is nothing but the sampling frequency. So we know that Fs is called as the sampling frequency, which is the reciprocal of the sampling period. This is called as the sampling frequency. So sampling period is the spacing between the samples, and the rate at which these samples appear is called as the sampling frequency. Now let us look at the concept of sampling theorem. We understood what is sampling. Now let us look at the important concept in signals and system, which is sampling theorem. So what is the statement of sampling theorem? It states that a CT signal can be represented in its samples and can be exactly reproduced from its samples if it is sampled at a sampling frequency which is greater than twice the maximum frequency in the signal. Let us focus at each and every part of it. What it says is that if you are transforming a CT signal into a DT signal, you need to properly select the sampling frequency. So as per sampling theorem, the sampling frequency should be greater than twice of F max. As per sampling theorem, we should choose the sampling frequency to be very large than twice of F max. Minimum it is equal to twice of F max, because that's why we say greater than equal to. So minimum value of sampling frequency is twice of F max, and that minimum value is called as the Nyquist rate. Okay, the minimum value of the sampling frequency, which is Fs is equal to twice of F max, is called as the Nyquist rate. But as per sampling theorem, the sampling frequency, a better sampling frequency is one which is very large than twice of F max. Now, what are the rest of the statements of sampling theorem? The very first statement is sampling theorem it states that a CT signal can be represented in its samples. So sampling is basically a process of transforming a CT signal into its samples. And what it further says is that we from these samples the CT signal can be recovered back. So if we choose a appropriate sampling frequency, then we can transform from DT signal back to CT signal. So what is the basic guidelines of sampling theorem is that sampling theorem first of all says is that a CT signal can be transformed into a DT signal by sampling, and you can reproduce. It means that you can get your CT signal back. We can get the CT signal back from DT signal if we maintain a proper sampling frequency. This is the concept of sampling frequency, a sampling theorem, right? It says that if we can obtain DT signal from CT signal by the process of sampling, and we can recover back. It means that from the discrete time domain signal we can get back the CT signals, right? We can reproduce the CT signal back from DT signal, but this is possible only if we have maintained a condition on the sampling frequency. And what is the condition? That The condition of sampling frequency should be greater than twice the maximum frequency. And what is this Fmax? Fmax is the frequency of the signal that you are sampling. Right? Fmax is the frequency of the signal that you are sampling. Right? And the minimum sampling frequency as per sampling theorem is Fs can be minimum twice of Fmax. And the minimum sampling frequency is called as the Nyquist rate. And the reciprocal of this minimum sampling rate is called as the Nyquist interval. Right? If I take the reciprocal of minimum sampling frequency, right, we get the maximum sampling interval, which is the Nyquist interval. Now let us understand the sampling theorem in more detail. So for this, let us look at this particular figure. So there are total 6 figures here as shown. The first column of the 3 figures indicates all the time domain representations, whereas the second column of the figures shows the frequency domain representations. So the left hand side signal is the time domain signal, and the right hand side signal is its equivalent frequency domain. So this is a CT signal and this is its equivalent frequency domain. This is the train of impulse and this is its equivalent frequency representation of the train of impulse. This is a sampled signal and this is its frequency domain. So there is a correlation between the time domain and frequency domain signals. So the time domain signal is represented in first column and its equivalent frequency domain is represented in the second column. Let us start the discussion with the CT signal. So we have been given a CT signal and we are expected to sample it. So for sampling a CT signal, we need a train of impulse. So you could see here we have taken a train of impulse which is called as a signal ST. So we are multiplying the CT signal XT with ST, and we know that when we multiply the train of impulse with a CT signal, the location of the impulse decides the location of the DT signal that we obtain. So at every impulse we get an output and the output sample has a magnitude which is equal to magnitude of the CT signal because all the impulses have unit magnitude. So these impulses do not change the magnitude of your CT signal. What they affect is the position. These impulses just gives us the instances at which the DT signals will appear. At every sample, you get the output sample which is equal to the magnitude of your CT signal. And this is how we have obtained a sampled signal. This is your sampled signal. Now let us look at the frequency spectrum of the signal. So for the given CT signal, let us say that this is its equivalent frequency domain representation. So this is the frequency spectrum of your CT signal obtained by applying Fourier transform on the signal. So if we find the Fourier transform of this particular CT signal, we get its frequency domain representation. Similarly, this is the train of impulse which is repeating after every Ts amount of time. When we find its frequency spectrum, we get again a train of impulses but which are repeating after every Fs amount of time. So you could see here this frequency spectrum of train of impulse is nothing but again a train of impulses but repeating after every Fs amount of time. So reciprocal of Ts is Fs and that's why we get samples which are repeating after every Fs amount of time. Right, so this is the first sample at 0. This is the second impulse which is appearing at Fs. This is the third impulse which appears after 2 Fs. Next will be the impulse which will appear after 3 Fs. So this is the characteristics of frequency spectrum of your impulse train. Right, and then we have the sampled signal which is obtained by multiplying the CT signal with the train of impulse. And when we look at the spectrum of this sampled signal, the spectrum appears as shown here. Right, the spectrum appears as shown here. If we now do a close comparison of the spectrum of the original CT signal with the spectrum of the DT signal, what is the change we observe? We observe that we get a similar frequency spectrum but which is continuously repeating, right? If I compare the frequency spectrum of the CT signal with the spectrum of your DT signal, what is the difference between these two spectrums? We observe that the spectrum of CT signal becomes repetitive in the spectrum of the DT signal, whereas the information remains the same, but we see a periodic repetition because of the process of sampling. And why do we get such a repetitive elements of the original spectrum? Let us analyze this with a mathematical analysis. Let us look at now how do we get such a kind of repetition of the original spectrum when we sample the DT signals. So for this, let us look at some mathematical analysis. Let us start with the train of impulse. So train of impulse, as discussed earlier, is nothing but impulses which are shifted in time. So all these infinite impulses which are shifted in time can be represented within the mathematical identity as shown here. So it's the impulse which is shifted by n ts amount of time, where n takes minus infinity to plus infinity time. Right? So if n is 1, you get the impulse located at t is equal at delta t minus ts. With n is equal to 2, you have the impulse at t delta t minus 2 ts, and so on. So combining all these shifted impulses, we get the train of impulse. So this is the mathematical representation of the train of impulse, where we have got all the impulses which are shifted right from minus infinity to plus infinity, and combining all those, the summation shows that we have combined all these train of impulses to form one signal, which is signal ST. Now, what is the role of this train of impulse in sampling? Is that we multiply the CT signal with the train of impulse. The role of impulse is that we multiply the CT signal with the train of impulse. So that results into the discrete signal. So let me call the discrete signal as XS of t. So multiplying the CT signal with the train of impulse results in the discrete signal. Let me substitute ST. So we know that the signal ST is the train of impulse. So let us replace ST with the equation as shown here. Now what do we know? Wherever there is an impulse, that results into an output of the magnitude which is equal to the magnitude at the time of sampling, right? So with respect to the figure, if I analyze, what does this mean? It means that if this is the impulse I'm talking about, the output of this impulse when multiplied with the CT signal will be the magnitude of that CT signal at the point of sampling. So what it gives me in the output by the product of this train of impulse with the CT signal is nothing but the samples which are equal to the magnitude of your CT signal, and therefore we can write this particular product, which is xt into delta t minus nts, as we will show this product as x of nts into delta t minus nts. Instead of xt remaining outside, I can show that this product of xt with the shifted impulse is equivalent to obtaining the samples of magnitude at the instant of sampling. So if I now say that my n is 1, so where is the impulse located? The impulse will be located at t minus Ts. So the impulse will be located at T minus Ts. So what would be the magnitude of this impulse with the signal xt? It will give me the magnitude of the signal xt at x of ts. When n is 1, I get the magnitude of the signal at x of ts. So this position of the impulse gives me the output at those positions located by the impulse, and therefore we can write it as x of nts into delta t minus nts. Now we will represent the same product in frequency domain. So this product in frequency domain becomes multiplication, turns out to be convolution. So multiplication theorem, we will apply the theorems of Fourier transform. So multiplication becomes convolution in frequency domain. So in frequency domain, XST is denoted as XSF, x of nts is nothing but x of f, and delta t minus nts, this signal, this is the train of impulse, which I'll denote it as s of f. So it's the multiplication of signal xt with the signal st. So we can now say that instead of multiplication, it is the convolution of the frequency spectrum of signal xt with the frequency spectrum of signal st. So let me say the frequency spectrum of xt is x of f. Let me say that the frequency spectrum of st is s of f. So multiplication becomes convolution. So you could see here, instead of representing the signal in time domain, the same signal is represented in frequency domain, that changes the multiplication into convolution operation. Now let us look at the frequency spectrum of the train of impulse. So frequency spectrum of train of impulse is nothing but all the impulses shifted by ts amount of time. So if we find the Fourier transform of the train of impulse, what we get is all the impulses shifted in frequency domain, and therefore I can write the mathematical equation of the train of impulse in frequency domain as sum of all the impulses shifted in frequency domain by n f of s. So the samples appear at 0, at fs, at 2fs, and so on, and therefore I can write the mathematical equation of the impulse train, which is in time domain, in frequency domain, as sum of all the impulses shifted in frequency domain. Now, if I substitute this s of f into the equation 1, what do we get? We get the output discrete time sampled spectrum of discrete time domain signal as x of f convolved with, instead of s of f, I'll replace s of f, that is frequency spectrum of train of impulse, by its impulses shifted in frequency domain. So I'll substitute this s of f by this term. Now we are going to simplify this convolution. We have to simplify this convolution. So how is this convolution simplified? So we have now the convolution of x of f with the train of impulses shifted in frequency domain. We can take 1 by ts constant outside, and now we are going to perform convolution of the input signal spectrum with the spectrum of the train of impulse. And what we know, we have a convolution property wherein convolution with impulse simply shifts the signal. We know that convolution with impulse simply shifts the signal. So convolution of x of f with the shifted impulses results in the input signal shifted by these points, by these frequencies, right? So we have now, instead of this convolution, we can express this convolution as the signal spectrum x of f, the signal spectrum x of f shifted at these frequency instants. So it becomes x of f minus f of s, right? So this convolution is represented by this mathematical identity, and what is the meaning of this mathematical identity is shown here by expanding the summation. So we have expanded the summation. Look at each of the term. So when my n is 0, what do we get here? If I expand this summation for various values of n, and let me look at the term especially at n is equal to 0. What do we get at n is equal to 0? We get simply x of f. And what is x of f? X of f is the frequency spectrum of the original CT signal. So we have one frequency content in x of s, XSF is nothing but the frequency spectrum of the sample signal. So let us mention it clearly here. What does XSF means? XSF means it's the frequency spectrum of sample signal, right? It's the frequency spectrum of sample signal, right? And what is XF? XF is nothing but it's the frequency spectrum of CT signal. It's a frequency spectrum of CT signal, right? And then therefore we are now looking at the analysis of frequency spectrum of sample signal. So frequency spectrum of sample signal consists of what? Frequency spectrum of sample signal consists of one component, which is frequency spectrum of CT signal. Let us say this is the component. This is your X of F, right? This is your X of F, original frequency spectrum of your given CT signal. But this is not only the component which is present. I have this component wherein X of F is shifted by Fs amount. Here it is advanced. It means that X of F plus Fs is nothing but this particular signal which is advanced. The same signal is shifted on the right hand, on the left hand side. So this is X of F plus Fs. Definitely what this must be then? This must be X of F minus Fs. This component must be X of F minus 2Fs, and so on. So therefore, what this equation actually tells me is that the frequency spectrum of the sampled signal consists of the original frequency spectrum, which is shifted by Fs amount. So therefore you get a repetitive frequency spectrum when you obtain the frequency spectrum of the sampled signal, right? So let me go back to the previous figure and correlate the discussion with respect to this figure, right? So what we did, friends, by this analysis we have obtained the frequency spectrum of the sample signal, right? We were interested in knowing what are the frequency components present in the sample signal. If this is my original CT signal, which I have sampled by multiplying it with the train of impulse, I have got the sampled output. Then if this is the frequency spectrum of the CT signal, then what is the effect of sampling on the frequency spectrum of the sampled signal? So if this is the frequency spectrum of the original CT signal, and if we sample the CT signal and make it discrete, what is the effect on the frequency spectrum of the CT signal? We observe that the frequency spectrum of the CT signal becomes periodic, and this is what we mathematically proved, why we are getting a periodic repetition of the signal, right? That is what we proved. How do we get this? So this analysis is what we did by showing that the frequency spectrum of the sample signal has the original frequency spectrum of the of the given CT signal along with its shifted version. So all these are the shifted versions of the original spectrum, right? So here is the analysis of the sampled signal spectrum. So all these signals which are shown here is nothing but the spectrum of the sampled signal for various cases of sampling frequency. I have analyzed, this is the output. Now we know that this is the output of the sampled signal. This is the frequency spectrum of the sampled signal, right? Now we know that each of this spectrum is repeating. We have got a periodic repetition. Now how can this repetition be? The repetitions can be of each of these forms. And why do we get such kind of different repetitions? These repetitions differ according to the condition on the sampling frequency. So if I take the first case, wherein if my sampling frequency is very large, by it is very large, then twice Fm. If It is my first case wherein my sampling frequency is very large than the twice of FM as per sampling theorem. What is the effect on the sampled frequency spectrum? So you could see that these repetitive spectrums are at a very large distance. There is a spacing observed between the repetitive samples because in the first case, I have taken sampling frequency to be very large. In the second case, if I make my sampling frequency to be twice of FM, if I reduce my sampling frequency now and I choose a sampling frequency which is merely equal to twice of FM, then how is the repetitive spectrum? The spectrum is like this because now the spacing is reduced, right? Each of your repetitions, if you observe carefully, is repeating after every Fs amount of time here, right? Each of these repetitions are after every Fs amount of time. If we reduce this Fs, it means that these spectrums will come closer. So, for the condition when Fs is equal to twice of Fm, this is the nature of the output of the sampled signal. And in the third case, if I further reduce my sampling frequency, here I had taken a very large sampling frequency. In the second case, I had made my sampling frequency to be merely equal to twice of FM. And in the third case, if I make my Fs to be very large, then very less than twice of FM, this is the effect on the spectrum. What do I see? I see a spectral overlap. This is said to be a spectral overlap. And why do we get this spectral overlap? We get this spectral overlap because we have reduced the sampling frequency less than twice of FM. It means that for this particular case, we have not satisfied the sampling theorem because this is the condition which is not satisfying the sampling theorem, right? So this condition Fs less than twice Fm is not satisfying the sampling theorem because what does the sampling theorem actually is? Sampling theorem says that sampling frequency should be very large than twice FM. So if we maintain the sampling frequency, we get this output, right? Here we have satisfied the sampling frequency. So case 1 is the case where we have satisfied the sampling theorem. Is it not? Because we have chosen the sampling frequency to be very large than twice FM. And in the third case, we have not satisfied. And in the second case, we have merely satisfied the sampling theorem. Right? So we have two extreme cases wherein we have satisfied the sampling theorem and in the last case we have not satisfied the sampling theorem. So this clearly tells us the significance of sampling theorem, friends, right? That if we choose a sampling frequency, according to sampling theorem, we get an output which is of this form where there is no spectral overlap. And if we do not satisfy the sampling theorem, we get an output where there is a spectral overlap. Now the question is, what is the significance of such an output? So let us discuss it with respect to this example, right? What do we know? What does sampling theorem says? That sampling theorem says that we must be able to reproduce, is it not? There was one word in the sampling theorem which says we must be able to reproduce back the CT signal. After I transform the CT signal into DT signal by sampling, I must be able to recover back. I must be able to get my CT signal back from the DT signal, and that is possible only if we follow the sampling theorem. So look at the first case. So we know that this was the case when we had satisfied the sampling theorem, when sampling frequency was very large than twice of F max. Is it not? Now if we place a simple low pass filter here, right? This is a low pass filter with a cutoff frequency greater than FM, less than Fs. right? So if we place a low pass filter here, what we can do? We can easily separate out one of the spectrum, right? And if once we separate out the through low pass filter, actually we are cancelling the repetitions and we are selecting only one of the spectrum. And once we get this spectrum and apply inverse Fourier transform, can we get our original CT signal? Yes, we can definitely recover our CT signal if we properly select one of the repetitions, because our CT signal is having originally the spectrum as shown here, but there must not be any repetition. So how do we remove these repetitions of the spectrum? By applying a low pass filter. So if we place a low pass filter as shown here, what this low pass filter will do? Will discard these repetitions. Is it not? This low pass filter will discard the repetitions, only pass one band of the original spectrum. Once I get this original band of the spectrum, I'll apply inverse Fourier tool to this and get back my original CT signal. So I'm easily able to reproduce my signal, right? While applying a simple low pass filter, I am able to recover my CT signal back. Let me go for the next case. What has happened in the next case? In the next case, my Fs is twice of F max. The next case, my Fs is twice of F max. It means that here the spectrum is very close, but still there is no overlap. If I place my low pass filter in this form, I am still able to recover my one spectrum completely and discard the repetitions. Once I get my complete spectrum of the original CT signal, I can apply inverse Fourier tool to this and get back my CT signal. So in the second case also, by placing the low pass filter as shown here, I can still get my original spectrum. Discarding the repetitions, I can get back my original spectrum of the CT signal. Once I get the original spectrum of the CT signal, I'll apply inverse Fourier tool to this, because this is in frequency domain. I'll apply inverse Fourier tool to this and transform this into time domain, getting my CT signal back. So in the second case also, I am able to reproduce my CT signal as per sampling theorem. In both these cases I have satisfied the sampling theorem, right? And that's why I'm able to reproduce my CT signal. Now let me go for the third case. What has happened in the third case is my Fs is less than twice of F max. It means that I have not satisfied the sampling theorem, and therefore what has happened to my spectrum? My spectrum has an overlap, right? There is a repetition, and since the repetitions are such that I have my Fs is very small, these repetitions have been overlapped because I have chosen sampling frequency to be very small. I have not satisfied a correct sampling frequency while sampling the signal, and because of which what I observe is that I observe that I get a spectral overlap. And what this spectral overlap actually does, friends, this spectral overlap changes the shape of the spectrum. This spectral overlap actually changes the shape of the spectrum. So if you want to look at what will be the change in the spectrum, now my spectrum will be something different. My spectrum is going to be a modified spectrum because of this overlap. This overlap here, friends, you see this spectral overlap cancels the spectral contents, damages the spectral contents, and because of which there is a change in the shape of the spectrum itself. So if we want to understand this, the spectrum shape will be something like this now. Right? The spectrum will be modified, and we get a spectral shape which is entirely different from the original, right? This was my original spectrum, and this is now the modified spectrum. So the content, the shape itself has changed. The moment we say the shape of the spectrum has changed, what does that mean? It means that the content has changed. The frequency contents have changed. If the frequency contents have changed, can I recover my CT signal, original CT signal from its spectrum now? No. Right? Since the shape of the spectrum itself had changed, what I get when I recover will be something different from the original CT signal. Right? So we will not be able to recover back the original signal. So for this particular case, from such a spectrum, we are not able to reproduce, correct? We are not able to reproduce the original CT signal, right? And therefore sampling theorem plays a very important role in the process of sampling, right? Sampling theorem gives us a guidelines of what should be the sampling frequency one should choose while sampling the CT signal. If we choose a wrong sampling frequency, then it results in a spectral overlap. This spectral overlap damages the spectral content, frequency contents itself, and once the frequency spectrum content itself is hampered, we cannot get the original CT signal. So we are not able to reproduce the original signal, and therefore the sampling theorem states that your sampling frequency should be at least greater than or equal to twice of f max, so that you are able to reproduce your CT signal, friends. Right? So let me go back and revisit the sampling theorem statement. What was the sampling theorem statement? The sampling theorem states that we are able to represent CT signal in the form of its samples, and this is very important now. And now we understand, with this all this analysis, we understand the meaning of this statement, that we can exactly reproduce from its samples. We are able to reproduce the CT signal back from its samples if and only if your sampling frequency is greater than equal to twice of f max. This is the meaning of sampling theorem. And we understood, if we do not obey the sampling theorem, what it results into? It results into a spectral overlap, and this spectral overlap damages the contents, modifies the contents, and that's why we get a completely different spectrum. And that spectrum, when we apply inverse Fourier tool on this, we will not get our original CT signal, but the signal will be something different than the original CT signal. Right? If we transform such a DT signal back to CT signal, we will not get a proper CT signal. Instead, what we get is a complete different CT signal. Right? And that's the role of sampling theorem. That is the meaning of the statement of sampling theorem. So sampling theorem is nothing but a guidelines given to select a proper sampling frequency while sampling the CT signal. Now let us look at the term aliasing, which is associated with sampling theorem. What is aliasing? So, as we have seen, when we do not satisfy the sampling theorem, it means that when our Fs is less than twice of Fm, this is the spectrum that we get, where we observe spectral overlap. Is it not? If our Fs is less than twice Fm, we get an output where we observe spectral overlap. And this spectral overlap changes the basic shape of the spectrum itself. If the basic shape of the spectrum itself changes, we will not be able to recover the CT signal back, and that's why it says consequently XT cannot be recovered exactly from XST, and this is called as aliasing. This effect is called aliasing. So aliasing occurs. Aliasing occurs when sampling frequency is less than twice of FM, right? Overlap in the shifted replicas of the original spectrum is termed as aliasing, right, which refers to the phenomenon of high frequency component in the spectrum of the signal seemingly taking an identity of low frequency spectrum in the signal. What is the meaning of this particular statement? So this particular statement means that when we are not satisfying the sampling theorem, we are expected to have a spectral overlap. The spectral overlap modifies the complete basic shape of the spectrum, changing the frequency contents. Now, if I apply inverse Fourier tool on this and try to look at my CT signal, what happens is because of spectral overlap, the high frequency components in the signal change its identity and become equal to some low frequency content of the signal, right? What does sampling aliasing actually do? This spectral overlap that happens because we have not chosen a proper sampling frequency is changing the spectral shape, right? And this change in spectral shape results in entirely a different signal. So if we, especially where is the change happens to the high frequency components. So the high frequency components in this signal hampers, and these high frequency components appear when I take the inverse Fourier tool of this. What do I observe is that the high frequency components become or take the identity of low frequency components. So high frequency components will be identified as some low frequency component, and the meaning is that the high frequency component takes the identity of a low frequency component, right? Becomes similar. High frequency component becomes similar to a low frequency component, and that is the word alias comes from. Alias is what? If we look into the dictionary meaning of alias means similar to, right? Alias means a copy of, similar to, right? So what is similar to here? Since we have a spectral overlap, as we do not satisfy the sampling theorem, right, we get a complete different signal, right? And what is the meaning of complete different signal? Is that when we have a spectral overlap, the high frequency components in these signals do not remain the same. Instead, they get changed and high frequency components become low frequency components, right? High frequency components are identified as low frequency components because of improper sampling, and this effect is called as aliasing. Now, how do we avoid aliasing? So aliasing is not at all acceptable in sampling process, right? So aliasing can be avoid aliasing. So aliasing can be avoided by using a pre-aliasing filter. What is the meaning of this? That before we do sampling, we should put a filter through which we will pass the analog signals, and then we will perform sampling. So A to D conversion is nothing but sampling. So before we do sampling, we should have a filter. Why should we have a filter? Suppose if we are sampling at a sampling frequency of Fs. Suppose this A to D conversion is nothing but a sampling process. So if there is a sampling process, there is some sampling frequency associated, right? So if this is the sampling frequency, what is the maximum input frequency we should allow so that there will not be aliasing? So the maximum frequency that we can allow, as per sampling theorem, what do we know? As per sampling theorem, we know that Fs must be at least equal to twice of F max. So now I know my Fs. So maximum frequency I can apply. So the maximum frequency we can apply is Fs by 2. So it means that if we put a low pass here with a cutoff frequency Fs by 2, right? If I put a low pass filter with a cutoff frequency Fs by 2, what it will do is it will pass any frequencies above Fs by 2. All the frequencies of the input signal will be restricted to Fs by 2, and therefore if I now sample such a signal at a rate of Fs, we will not be having a aliasing problem at all, because we have taken care of it prior to sampling. We have not passed any frequency to this A to D conversion where we will be doing sampling that is above the sampling frequency, right? Hence, we will not have any situation created here during the sampling. We have, which will have a condition wherein we have overcome, where we have, we are above the sampling frequency. We will always have a condition which wherein our sampling frequency will always be satisfied, because our maximum frequency is never exceeding Fs by 2. Therefore, we will correctly satisfy the sampling theorem with this low pass filter. We will never have a situation of aliasing occurring in the sampling process. So this is the first corrective action we can do to avoid aliasing in the sampling process. How do we do that? Putting a low pass filter. This pre-aliasing filter is nothing but a low pass filter. Okay, this is a low pass filter. So if we place a low pass filter and pass the analogs from the low pass filter and then give it to a system that is performing sampling, we will never have a situation wherein we have not satisfied the sampling theorem, and we will never have aliasing occurring. We'll connect a low pass filter with a cutoff frequency Fs by 2. So this low pass filter having a cutoff frequency Fs by 2 will avoid the aliasing in the sampling process. And what is the second way of avoiding aliasing is always take a care on the sampling frequency. Maintain a proper sampling. If we maintain a proper sampling frequency, we will never have aliasing effect occurring in the sampling process.